Gxy is the set of all elements G in G, such that the source of G is X and the target of G is Y. Here we have all the morphisms that starts in X and ends in Y. Note that the Gx is a group. This is the group with source and target is equal to X. And this group is called the Isotropy Group associated to X. We set also G square between parentheses here, has the set of all elements here in G times G that SG is equal to TH, and these are the pairs that are composable here in the groupoid. And it's clear that the source of G is G inverse G, the target of G is G inverse, SGH is the source of H, and the target of GH is the target of G. Well, let's talk about connected groupoids now. A groupoid G is said to be connected if for each pair of objects there is a morphism between them. This is the set of morphisms that starts in X and ends in Y. And this is a connected groupoid. And any groupoid is a joint union of connected subgroupoids. The idea is pretty easy here. Let's see. For instance, we have here objects of a groupoid. Then, for instance, we have here objects that are connected between them. Here we have another component, and this one is completely alone. So the union is one connected component, another connected component, and another connected component. When we have the union, this is G. That's why it's said here. We take the objects here, and we take the morphisms between them, and this is the connected component. And a connected groupoid is completely determined by any of these isotropy groups and its objects in the following way. Here I have to introduce a new definition. A transversal in G for an object X is a map, which call tau, from G0 to G, where we write tau applied in Y, it's tau Y, such that tau Y is an element that starts in X and ends in Y for all Y in G0, and tau X is X. And then we have projections here where, well, it's easy to computate this. Now consider the following groupoid. Here, what is behind the theory that a connected groupoid can be viewed has this decomposition here. And here we are showing what is the isomorphism that to show this. And this isomorphism uses the transversal. I write it in the next slide. So we have an isomorphism of groupoids phi between G and H, and it is the identity at the level of objects, and at the level of morphisms, we have this following. When C, YZ applied in G is YZ and tau G. The transversal, the idea of the transversal, it's something like there. We have objects here in a groupoid, in a connected groupoid, which means that all these objects are connected between them, and then pick one of these objects, for instance, X, And then the transversal is these elements here, and so on, which means that the transversal here, one transversal is for an element X, is this set of morphisms that starts in X and end in Y. Well, let's go to partial actions now. Here I will introduce the notion of unital partial action of a groupoid. This is not the more general, and I'm talking about partial actions of a groupoid on a ring. I will talk just about unital partial actions. That's why we need in Galois theory. So a unital partial action of a groupoid on a ring is a family of pairs SG and alpha G, where SG is a two-sided ideal generated by a central idempotent 1G of S, and alpha G is an isomorphism of rings between these ideals that is satisfied these axioms. It's pretty similar to the definition of partial actions of group. But here, the ideals, we are dealing with ideals of ideals, instead ideals of the whole ring. And the composition will partially define it, because here we have a groupoid, and in a groupoid, the elements don't need to be composable all the time. So we ask that 1G, 1TG is equal to 1G, and this is equivalent that SG are contained in STG. We ask that for each X in the set of objects, alpha X is equal to identity SX, and these two last axioms are saying to us that the composition, first of all, is possible just in the appropriate domain, not in all the time. And the second thing that we can conclude about this is that the alpha GH is an extension of alpha G, alpha H. Well, the items 3 and 4 above imply that alpha GH is an extension of alpha G, alpha H, and when we have this equality, we say that this partial action is global. So from now on, when I say partial action, I mean unital partial action. A remark, so let alpha be a partial action of a groupoid on a ring S, X be an object, and H is a subgroupoid of G. Then the isotropy group GX acts partially on the ideal that are indexed by the elements in X via this. This is a partial action of group, because here we're treating about a group. If X in H0 is an element here, then alpha restricted to HX is a partial action of HX on SX, and in this case, alpha AGX is the restriction of alpha GX to the subgroupoid HX. And if we have this hypothesis, which we're asking that S is a direct sum of its ideals, and H is a subgroupoid of G, then we can consider the restriction alpha H to this subgroupoid, and then we have a partial action now we're treating about a groupoid on this ideal SH. Here it's direct sum of SZ, where Z are in age 0. Then we finally will define the partial actions of group type. The definition of group type is due to Baggio, Pax, and Pinedo. This is the reference. And I will say now what is a partial action of group type. So a partial action of this definition here is first for a connected groupoid. Next, we will extend it to any groupoid. So of a connected groupoid G on S is called group type if there exists an element X in G0 and a transversal in G for an object X, such that the ideal S tau Y inverse is Sx, and S tau Y is Sy for all Y in G0. The name of a group type is due to the fact that in this work, they showed that the skew groupoid ring, the skew partial groupoid ring of this kind of partial actions is realized as a skew group ring. This is showed here. Well, any global action on G of G on S is of group type. In fact, lemma 1 of this work of Baggio and Pax implies that SG is equal to STG when the action is global for all G in G. Hence, the condition 1 is satisfied, and alpha is of group type. And for more examples of group type partial actions that are not global, I refer the previous reference here. Where is here? In this reference, one can find more examples. A remark, assume that alpha is a group type partial action of H on S, and consider tau a transversal in G for X, such that the condition 1 is true. Given another object Z in G0, we fix the set gamma, which here is tau Y, tau inverse Z, where Y is on G0. And by a remark of the same reference before, gamma is a transversal in G for Z that also satisfies condition 1. Thus, the notion of group type partial action does not depend on the choice of the object X. And now we will extend the notion of group type partial action to groupoids that are not necessarily connected. In this, we are entering in the work that me, Dirceu, and Alveri did. Let G be a groupoid, and this is the composition in connected components of G. This extension is pretty natural. Assume that alpha is a partial action of G on a ring S, and that S is a direct sum of its ideals. In this case, for each class here, we have a partial action alpha Y of GY on SY, where SY has this decomposition in the direct sum, and the partial action here is in this, has these ideals and this isomorphism. This is the composition we used in all our work. So let G be a groupoid, any groupoid not necessarily connected, and alpha partial action of G on the ring S. We say that alpha is group type if the partial action alpha Y of the connected component GY on SY is of group type in the sense of the definition 2.3 for all Y in this, all class Y. So this is the definition of any group type partial action. So we can start to talk about Galois theory now. Galois correspondence for global action was given here. It's a work with me and Pax. And now the next step was to think about the correspondence in the partial case. Unfortunately, we did not make the correspondence for any partial actions, just for partial actions of group type. This general case is still an open problem. Let G be a finite groupoid and alpha be a partial action of G on a commutative ring S. Our extensions are commutative, so we are dealing with the commutative case. We will assume that SG is S1G, where 1G is the central idempotent of S. 1G not equal to 0 for all G in G. So we have the definition of a Galois extension. And this ring extension is called an alpha G partial Galois extension if, first of all, R is the fixed part by the action of G. I did not define the fixed part. Okay, this is the fixed part. And remember here that we are talking about unital partial actions. And there exists a positive integer m and elements a, I, b, y here in the commutative ring S, such that this condition happens. This set is called the partial Galois coordinate system of S over R. So let R be the fixed part by the action of G, and Rj is equal to the fixed part by, here we are talking about the connected component associated to the composition of G in connected components. So here is this fixed part for all components. Then this extension is a partial Galois extension if and only if this extension Sj over Rj is an alpha J partial Galois extension for all J between 1 and R. Oh, here's the definition of invariant elements, which is basically the same that the partial actions of groups. It's the elements that are invariant by the action of the groupoid G, with here the unital partial actions. Given a subring T of S, we'll denote by GT the set of elements of G which act trivially on T, which means that GT is the set of the elements G in G, such that alpha G applied in T, 1G inverse is equal to T1G for all T in T. And with this notation, let T be the fixed part by a subgroupoid alpha H, and Tyj is equal to the fixed part. Here is Isotropy Group associated to the connected component for all J in between 1 and R, and G in G. So the following assertions are satisfied. GT is a wide subgroupoid of G, which means that the GT0, the set of objects of GT, is the same of the set of objects of G, if and only if GYJ Tyj is a subgroup of this isotropy group for all associated to all the connected components. And GT is equal to H if and only if GYJ Tyj is equal to HYJ for all J between 1 and R. And recall that a unital ring extension T over R is called separable if the multiplication map is a splitting epimorphisms of T modules. This is one of the definitions of separable algebras. This is equivalent, for instance, to saying that there exists an element E here, such that TE is equal to ET for all T in big T here, and M applying E is 1T. Such an element is usually called as idempotent of separability of T over R. We usually use this definition in Galois theory, using this idempotent of separability. This is more usual. Just we now fix some notations. This set is the set of a subgroupoid of G, such that alpha restricted to this subgroupoid is of group type. And we put an double V here to take the subconjugate subset here, such that age is here, which means that alpha restricted to age is of group type, and age 0 is equal to G0, which means that the age here is wide. We need to define the set because that is the set which appears in the Galois correspondence. So take an subgroupoid here, which means that it's wide, and when we restrict the partial action to age, it is of group type. T is the fixed part by the action of age, and R is the fixed part by the action of the whole groupoid G. For each J between 1 and R, consider this fixed part by the action of the isotropy groups here. And Ryj is the fixed part by the action. Here is the subgroupoid of the group. This is a subgroup of the group of isotropy. Then the following statements are equivalent. This extension is separable, which means T is separable of R, if and only if each of its parts are also separable. And another definition to give a Galois correspondence is the concept of alpha strong. So let T be a subring of S, and Ty is equal to T1y for all y in the 0. Then the subring TH of SH will be called alpha GYZ is strong if for any G and H here, which means that these are morphisms that starts in Y and ends in Z, such that G inverse H are not here, and for any non-zero idempotent E in this union, there exists T Y here in big Ty, such that this inequality difference holds. And we shall say that T is alpha strong if Ty is alpha GYZ strong for all objects that are in the 0. So this is how we define alpha strong in this case. This proposition shows that here, the second axiom that appears here is the definition that we gave for alpha strong in the global case, me and Pax. And here we show that these definitions are equivalent when we are treating about an subgroupoid here, which is a wide subgroupoid such that when alpha restricted to age is of group type. So under this condition, we have that T is alpha strong if and only if this condition holds, which is exactly the same definition that we gave in the global case. And this is also equivalent to Tyj is alpha G Yj strong for all J and between 1 and R. So in the next two propositions, we established the Galois correspondence. We first did it for the connected case, and then with one more step, we extended to all the whole groupoid. Let S be an alpha G partial Galois extension of R, which is the fixed part by the action of G. Age and subgroupoid here, which is wide, and when we restrict it to alpha to age is of group type. And T is the fixed part by the action of age. Then we prove that T is R separable and alpha strong. And also GT is equal to age. Then when we are taking here, T has the fixed part by the age, and we can prove that it when apply it, we have that it is in the set of R separable and of strong subalgebras of S. And by the other side, let S be an alpha G partial action extension of R. T and R separable and alpha strong subring of S such that GT is equal to age, where age is the subgroupoid here. Then, in this condition, we have that S alpha age is equal to T. Here, we have to ask that GT is equal to some subgroupoid here. Because if we don't ask this, we don't have the objective. It's a thing that we thought, and well, we have to ask this to the correspondence be objective. And so in this hypothesis, we show that S alpha age is equal to T. And so we have just fixing some notations that RB S alpha G and denote by BS the set of all subrings T of S which are R separable, alpha strong, and moreover, GT is equal to age for some subgroupoid age which is wide, and when we take alpha restricted to age, it is of group type. And with this notation, we have finally Galois correspondence. So the correspondence is here. Alpha G, which is the unit of partial actions of group type of a finite groupoid. The groupoids are finite here. I didn't not mention it, but it's always finite. Of a finite groupoid G on a ring, on a commutative ring S, such that the SG it's equal to S1G, and 1G is not equal to 0 for all G in G. If S is an alpha G partial Galois extension of S alpha G, then there exists a bijective correspondence between the set of wide subgroupoids such that when you take here a subgroupoid and restrict the action to the subgroupoid, it is of group type, and the set that I described here, the BS. And this correspondence is given by, for each age we take here, we associate the fixed part by the action of age. It's the Galois map. It's almost universal. And the inverse here is given by take a subring T of S, and we associate the subgroupoid GT. And in this hypothesis, this is a subgroupoid, which when alpha restricted to GT, it is also group type partial action. And then we have this one-to-one correspondence. And the problem of determining a Galois correspondence for partial groupoid actions, not necessarily of group type, remains an open question. Maybe the correspondence my guess is that it's a one-to-one between any wide subgroupoid and all the algebras that are separable and bit strong. It's a natural way, it's my guess, but we did not prove the general case, just the case of group type. And here I have some references. This is the reference when it was defined partial actions of groupoid of Gestel and Pax. Here it was the reference which was defined the group type partial actions. Here is our work that are available in the archive. And here is the work when we treated about the global case, the Galois correspondence for global groupoid actions. Okay, it was pretty fast. Okay, cough break. Thank you.
Let's have some questions first. So, Liese? Oh, sorry.
Thaisa, I was wondering, because all the groupoids you are dealing with are finite,
Yes.
you could consider instead of partial actions of these groupoids, partial actions of the weak Hopf algebra of the groupoid, and then there is a theory developed by Philippe and Glauber about the partial action, and then you participate the Galois correspondence. Well, in fact, for a week, there's not done yet, but I think could be only a step forward in that direction.
Yes, in that work, we just made several equivalents for the definition of Galois extension for partial Hopf algebras, but not the Galois correspondence. And this is a...
No, yes, you did the Galois correspondence for partial actions of Hopf algebra.
No,
this needs to be
no,
weak.
we did not make the correspondence for Hopf partial, just the equivalences of the definition.
I see. Mm.
So there's one more step, and then to weak Hopf algebras,
Yes,
I
in
believe
fact,
it's a little more complicated.
This correspondence for even for Hopf-Galois global case, this was a complicated theme which was discussed some time ago, and I think there's not a very good correspondence theorem for this thing in.
I believe that's not easy to do this because nobody did yet. I don't know which is the correspondence for a partial Hopf algebra.
Correspondence is tricky. Okay, thank you.
All right, more questions? I have one. So when you said the group type partial action of groupoids, so these are actual groupoids that they behave like group actions? So you can...
More or less, the skew groupoid ring for this kind of partial action can be realized as a skew group ring.
A skew group, oh, I see. So you can bring them results from there and apply here?
Yes. One question that I don't know, and I asked for Dirceu and also Hector, is that this kind of partial actions is the only class of partial actions that can be recovered using partial actions of groups.
Yeah.
I don't know if it's an if and only if problem.
Right.
The reciprocal is, I don't know if it's true.
Okay, right. So also with a student of mine a while ago, we realized the Leavitt path algebras as a partial skew groupoid ring of the groupoid of, well, it's the free group of the edges, but just given a groupoid structure. So is that, do you know if that action is, have you ever looked at it? If that action is of group type? This action, when you do like what Gilles was doing today, instead of looking at a free group, you can kind of modify it a little bit to get it as a groupoid. Would that action be a group type? I guess yes.
I don't know, and I don't remember what is this partial action, but maybe I can see the
The
definition.
action on the paths, right? You just have action on the paths, and you have the free groupoid on the paths. And then you have an element, let's say a path, and you
Well,
just
to-
look at all the
we
paths that
can-
start with it and so on.
Well, we have to take a transversal to be of group type if it's possible to take a transversal. I don't know, Daniel. I really don't know if it's possible.
Okay, yeah, it's just wondering.
Okay, I can think of.
All right. Okay, any other questions? If not, let's thank Thaisa again.
Thank you.
We'll resume at 4:20, right? For Francesca's talk, she'll be speaking from Italy, so I don't know what time is there. It must be 8 o'clock, I guess.